Now, this actually, what is stated here is universal gravitation. Now, universal gravitation, our Earth's gravitational pull is one particular type of gravitation. It's the gravitation between the Earth and our body. Okay. But in general, this gravitational force exists between any two objects or any two particles, even right down to the molecular or atomic level, right? So let's say two atoms or two molecules, they are very close together, they have gravitational attraction between them, right? It exists not only between the earth and our body. Between the earth and our body is one particular type of gravitational force. So what is stated by Newton here is universal gravitation. So universal gravitation means even let's say I'm holding a cup, I'm holding a cup here, there is gravitational attraction between the cup and my body. But because the distance is very far away, because this cup is very light and my body is very light, so the forces of attraction between the cup and my body is negligible. But theoretically, any two objects, any two objects, there exists gravitational pull between them. So how to define the size of this gravitational pull between two different objects? So we read this one, gravitational force, right? Or you read this, Newton's law.
Newton's law of universal gravitation states that every particle in the universe attracts every other particle with a force that is directly proportional to the product of masses of the particles and inversely proportional to the square of the distance between them.
Okay, right. Oh, the size of the force is like this. Let's say we have two objects. This first object, the mass is m1. This second object, the mass is m2. M1 and M2 can be anything, can be anything. Or it can be between two atoms. M1 is one atom, M2 is another atom. Or M1 is the earth, M2 is our body or objects on the surface of the earth. M1 can be the sun, M2 can be the earth, or M1 can be the earth, M2 can be the moon. Now, why we talk about moon and earth? Because the moon, the earth, the sun, they are very heavy. Their mass is very big. So the gravitational attraction between them is very big, right? It's very big. So that's why sometimes you have to talk about the moon and the sun and the earth and so on. Okay. Now, sometimes these two can be atoms. So at atomic level, these two particles here, they are very close to each other. Because they are very close, the force, although they have very small mass, because they are very close to each other, the force between them cannot be ignored. You have to take into consideration that force. Okay, so let's say that we have two objects or two particles in general, one with mass m1, another with mass m2. The distance between their center, it is measured from the center of the object. The difference between the center here and the center here is called R. It's called R. So the force between them is proportional to the mass m1 and m2. So the force is actually equal to m1 and m2. It means that the force is proportional to the mass of m1 and the mass of m2. But it is inversely proportional to the square of the distance between them. It is inversely proportional. How to explain this? To explain this, the force of attraction between these two particles will be will increase if the mass of m1 increases. That means if this is very big, then the force will also be very big. Second point, if the mass of m2 is very big, this m2 here is very big, then the force of attraction between them is very big. The third factor is the distance between the center of this object and the center. If the distance between them is small, the distance between them is small, the force is very big. If the distance between them, the two centers of the object, is very big, then the force between them is very small. That is the meaning of inversely proportional. So it is inversely proportional to the distance between them, but it is directly proportional to the mass of the individual particles, right? So, but what is this G here, right? When we talk about directly proportional and inversely proportional, the force cannot be exactly equal to this mass and the distance. Well, there is a constant in front. That constant is called the universal gravitation constant. This one, G, right? So this is a constant, a number, and this number is fixed for all objects. For all objects, this G is fixed. So it's just a number. It plays no role in affecting the force, right? So this G is the same whether it is on the moon, on Earth, the G is always the same, right? And from experiment, they conducted the experiment using two balls. I think now they kept it somewhere, the experiment. They conducted the experiment and they found out the gravitational constant to be 6.67 times 10 to the power of negative 11 Newton meter square per kilogram square. So this is the universal constant. Okay, so this is the formula lah, the product of the mass of the two objects divided by the distance between them, the square of the distance between them. Now, this particular formula, we can apply it to our case. That is something that we are familiar with. Okay, so let's say one of the object here is the Earth, and the other object here is any object on the surface of the Earth, right? We apply them to our Earth and objects on the surface of the Earth. So what will it be like? What will it be like? Okay. Now, the formula is this one. You look over the top here. In particular, if the two particles are Earth and object on the surface of the Earth, okay, then what will the force be? The force will be the weight of the object. The weight, that means the attraction by the Earth's gravitation on the object. So the force will actually be the weight. The weight is actually the force of attraction between the object and the Earth. Okay. Okay, one more time. If we apply this universal gravitational law to a particular case. That particular case is between the Earth and an object. So the gravitational force is actually our weight, the pull of the Earth's gravity on the object. So we call it W. We call it W. So the G will still be the G. The M1 will be the mass of the Earth because the Earth is pulling us. The M2 will be the mass of the object. Object can be our body, it can be a ball, or it can be a cup, it can be a cup. So that is the mass of the object. And the R, the distance between the Earth and the object is actually the radius of the Earth. You see, the Earth is a very big sphere. From the center of the Earth to the surface of the Earth, that will be the distance between them. That is also the radius of the Earth. Okay or not? So the weight is the product of the mass of Earth and the object. The distance between them is the radius of the Earth. Oh, I typed wrongly. Radius of the Earth. Okay, right. So I read through here one more time. If you think you have any doubt, you ask me, right? So the force now will be the weight of the object W, referring to this. The M1 is the mass of the Earth. The M1 here, the top here, become the mass of the Earth. The M2 is the mass of the object. We call it M lah. Then the R here is the distance between them. The distance between them is the radius of the Earth. Okay, right. So this is it. So you remember we call this equation 1. We call this equation 1. Then, but from our previous experience, the magnitude of the gravitational force acting on a mass m is called the weight of the object. And the weight of the object is given by mg, the mass times the acceleration due to gravity. Right? This is from our usual mechanics that we have learned earlier on. Weight is actually the mass times the g. W equal to mg. So comparing this first equation and the second equation mg here, this is W, this is also W. This is some formula here, and this is mg. But there is one similarity between this one and this one here. That is the m. So the m here will cancel with the m here. The m here in the equation 2 will cancel with the m in the equation 1. Thus, we have the g here equals to gme over r squared. So this is what we have. Okay. By comparing the equation 1 and equation 2, we see that our usual gravitational pull, our 9.8 meter per second square, is actually the universal gravitational constant multiplied with the mass of the Earth divided by the square of the radius of the Earth. That will give us our G on the surface of the Earth, 9.8 meter per second. Okay. Now using the same way, let's say if it is the sun, then it will be the universal gravitational constant multiplied with the mass of the sun divided by the square of the radius of the sun. That will give the G on the surface of the sun. And they have found out that the G on the surface of the sun is many times that of the Earth. This is 274, whereas on the Earth is only 9.8. The reason is because the mass of the sun is very big, much bigger than the mass of the earth. So they found out the G on the sun to be 274. Again, if you use the gravitational constant, multiply with the mass of the moon divided by the radius square of the moon, you get 1.62 meter per second square. Why so small? Because the mass of the moon is much smaller, so the gravitational attraction is much smaller. So we have arrived at these three numbers. Where this number come from? It comes from here. The G on the surface of the earth is the universal constant multiplied by the mass divided by the radius of the earth. Any questions so far? No. No,
No
then we go
questions, sir.
on. Huh? No,